Science has taken us beyond boundaries. And in this journey through science, man has started from a caveman, traveled continents, and today we are in this amazing scientific world. But now, the traveler is still alive, and now we're traveling the universe. We're traveling across the universe, from planets to galaxies, through nebulas to the Milky Way. And why are we traveling? We just want to find the laws that govern the universe. Is it true? No. Actually, man wants to invent the universe someday, and probably play God too. It's the curiosity of our ancestors that has brought us so far. But I think it all began with the one fundamental question. And what was that? Is there a connection between us and the universe? Wow, that was really cool, right? Or spooky. Okay, so before I explain all this cool, spooky, weird stuff, whatever you may call it, and before we travel to the deepest depths of our quantum world, I want you to forget whatever you've ever known so far and totally free your mind. So far you've learned that the atom is the smallest particle of any matter or any substance. But then later on, scientists actually told that the atom has a nucleus in the center and you have electrons revolving around it, like the solar system. Now, who proposed that? Yes, it was Rutherford who proposed that. But how did Rutherford first discover that there could be a nucleus in the center and electrons revolving around it, just like our solar system? How did he say that? So he did an amazing experiment called the gold foil experiment. So what he did do in that experiment was, you have the gold foil in the center, and he had alpha particles being bombarded on the gold foil, and you have a detector which was detecting whether those alpha particles were passing through the gold foil or not. And the discoveries of this experiment was completely about to change the way we perceive the atomic world. So this Rutherfords model basically gave us three major things. First thing was that Rutherford proposed that most of the space in an atom was empty. And secondly, he said there was a nucleus at the center and it was positively charged, and the electrons were revolving around the nucleus in circular orbits. Now, there's some problem with the Rutherfords model. And what is that? Actually, James Maxwell earlier proposed that if charged particles are accelerating, they would lose energy in the form of radiation. So in our case, if electrons were accelerating around the nucleus in circular orbits, they would actually lose energy and eventually spiral into the nucleus. I mean, in the sense, fall into the nucleus. In, how much time? In 10 raised to minus 8 seconds. So it's like the entire electrons would collapse into the nucleus in that small amount of time. But this was totally contradictory, because atoms are actually stable, because this particular phenomenon would totally contradict Rutherford's model, because that makes the atom unstable. So we really need a new model out there. But before that, what was James Maxwell's electromagnetic theory? What are electromagnetic waves? So let's get into that. So now let's discuss about James Maxwell's electromagnetic theory. So before that, we need to know what are electromagnetic waves. So as far as concerned, in the 18th century, Young, through his double slit experiment, confirmed that light behaved like a wave. So now that you know through the Young's double slit experiment that light behaves like a wave, but James Maxwell later on proposed in his electromagnetic theory that light was an electromagnetic wave. So what did he actually explain in his theory? He actually explained about interactions between charged particles and electrical and magnetic fields. And he said that when a charged particle moved with acceleration, it transmitted electrical and magnetic fields around it. And these fields were actually moving in the form of waves, which we call them as electromagnetic waves. So for more clear understanding, I would just want you to look at this picture, which actually suggests you how an electromagnetic waves would travel. So you have the electrical field, and which is perpendicular and in phase, you have the magnetic field, and that's the motion of propagation of the entire wave. So now let's discuss about the characteristics of electromagnetic waves. But wait a minute. Before talking about electromagnetic waves, let's just see what actually a normal wave looks like. So one thing you can observe is that there is a highest point and there's a lowest point for any wave. The highest point is called the crest, the lowest point is called the trough. And the distance between two consecutive crests or two consecutive troughs is actually called the wavelength, which is denoted by the symbol lambda and is measured in the unit meter. Next thing is that you have the height of the wave, which we call as the amplitude of the wave. And the next thing is we find that the wave has a frequency. So what is a frequency? The frequency is the number of waves or the number of crests that pass through a given point in a given period of time. So this is called as frequency, or denoted as nu. The unit of frequency is seconds power minus 1. Now, there's something called the wave number. The wave number is the number of waves that pass through a given length. That is the number of waves in a given length, which is denoted by 1 by lambda, which is, the unit is, meter power minus 1. Now that you know the basic characteristics of a wave, now let's go into the characteristics of an electromagnetic wave. Now let's observe the characteristics of electromagnetic waves. So in an electromagnetic wave, we have an electrical field oscillating perpendicular to the magnetic field. And both the electrical and magnetic fields are mutually perpendicular to the direction of propagation of the wave. Now, electromagnetic waves, unlike sound or ocean waves, can travel anywhere. They do not need a medium to travel. They can even travel in vacuum. And they travel everywhere with the same velocity, that is 3 into 10 power 8 meters per second, which is equal to the speed of light. Now that I told you, all electromagnetic waves travel at the speed of light, which means the velocity of every electromagnetic wave, as you know, is a product of its wavelength and frequency. Now, just varying these two components, wavelength and frequency, keeping the velocity of light as constant, we get a huge different variations of spectrum, which we call the electromagnetic spectrum. So different parts of the electromagnetic spectrum has different frequencies and wavelengths. And what part which we actually call as light or visible light is a very small part of the electromagnetic spectrum. Now, if you look at the entire spectrum, different frequencies have different usages. From the lower frequencies, which forms the radio waves, and then as we go higher, we go to the microwaves, which we're using in telecommunications. Now we have the visible spectrum, and as we go, we see the X-rays, which we use in the medical field. And as we keep going forward with higher frequencies, we have the gamma rays and the cosmic rays. So there's a huge spectrum of electromagnetic radiation and huge set of uses.